Welcome to a separable equation example. So in this example, our job is to find the general solution to cosine squared of x times y prime is equal to y squared plus 2y minus 3 times tangent cubed of x. So again, our first step is to separate the variables. So we had cosine squared x times y prime is equal to y squared plus 2y minus 3 times tangent cubed of x. We're going to go ahead and divide through by cosine squared x on both sides, as well as by that y squared plus 2y minus 3. So that the x's are on the right, the y's are all on the left. So we wind up with 1 over y squared plus 2y minus 3 times y prime is equal to tangent cubed of x over cosine squared x dx. Sorry, no dx. So tangent cubed x over cosine squared x. Our step 2 was to integrate both sides. So we have the integral of 1 over y squared plus 2y minus 3 times y prime is and then dx is equal to the integral of tangent cubed x over cosine squared x dx. The left-hand side just becomes the integral of 1 over y squared plus 2y minus 3 times dy. The right-hand side, we could rewrite this as the integral of tangent cubed of x times secant squared of x dx. So I wrote this problem to be a bit of review of our old integration techniques. This right-hand side lends itself perfectly to u substitution with our various trig integrals. So let's do that one first. So the integral of tangent cubed x times secant squared x dx. We can go ahead and set u to be tangent of x. And that means that du would be secant squared x dx. Again, if we have tangents involved and we have that even power on secant, then we can take advantage of that secant squared being the derivative of tangent. So this becomes the integral of u cubed du. So we get 1/4 u to the 4th plus c, or 1/4 tangent to the 4th of x plus c. So that's our right-hand side. For our left-hand side, we're looking at the integral of 1 over y squared plus 2y minus 3, all in the denominator, dy. This lends itself to partial fractions. This is 1 over, we have a y plus 3 times y minus 1 we will rewrite this as an a over y plus 3 plus a b over y minus 1. So again, here we're doing partial fractions. So we have that 1 is therefore equal to a times y minus 1 plus b times y plus 3. If we plug in y equals 1, then we get 1 is equal to b times 4, or b is 1/4. If we set y to be -3, then we have 1 is equal to a times -4, and therefore a is -1/4. So we are looking at the integral of -1/4 over y plus 3 plus 1/4 over y minus 1 dy. And that is simply -1/4 times the natural log of the absolute value of y plus 3 plus 1/4 times the natural log of the absolute value of y minus 1, and then plus, say, c1. So putting this all together, we have -1/4 times the natural log of the absolute value of y plus 3 plus 1/4 times the natural log of the absolute value of y minus 1 plus c1 is equal to, on the right hand side, we had 1/4 tangent to the 4th x plus c. I'm going to make it plus c2 here. And so this, if we set c equal to c2 minus c1, we again have -1/4 natural log absolute value of y plus 3 plus 1/4 times the natural log of the absolute value of y minus 1 is equal to 1/4 tangent to the 4th x plus c. If you wanted, we could simplify. So if we so note, you can simplify. If you like. Right? If we multiply by 4, we have natural log of absolute value of y plus 3 plus the natural log of the absolute value of y minus 1 is equal to tangent to the 4th of x plus c3, say. Sorry, that would be a negative natural log y plus absolute value of y plus 3 out front. If then we combine the logarithms, we could rewrite this as the natural log of the absolute value of y minus 1 over y plus 3 is equal to tangent to the 4th of x plus c3. Then we could do e to the on both sides if you wanted. So this will become y minus 1 over y plus 3 is equal to e to the tangent to the 4th of x plus c3. technically there's an absolute value here still. And then we can set C equal to e to the C3. And I'm actually going to make it could be positive or negative to absorb that absolute value. We wind up with y minus 1 over y plus 3 is equal to C e to the tangent to the 4th of x. There are ways to solve for y from here, but we'll go ahead and stop at this point. And so I should again say you can simplify if necessary, but you certainly do not have to. Much of the time, you're welcome to stick with the implicit solution. If it's an easy one to solve for y explicitly, then you might as well, but it's not always necessary.